Welcome to today's webinar. We are very sorry for the delay, but now we can get started. We want to analyze natural vibration and we want to perform an equivalent load analysis today. My name is Gerlin Schubert. My two colleagues, Stefan Frenzel and Andreas Hörold, they will help me throughout the webinar and they will answer all your questions you might have. So they try to answer all of the questions throughout the webinar, but just in case there are too many questions coming in, we will definitely answer your questions, but it might be after the webinar via email. This is the control panel you should see, and you can show and hide the control panel by using the orange button up here, and you can use the chat option to ask any questions. This is at the bottom here. So the theme of today's webinar, natural frequencies and equivalent static force analysis with RF-DYNAM Pro. I will give you a short overview and explain some features of the new DYNAM module. We will use an already existing structural system, which is a quite simple framework. We don't do any modeling today. You can watch other webinars if you are interested in this. We will perform a natural frequency analysis in RF-DYNAM Pro. We will import masses directly from load cases. We will perform mass combinations in accordance to Eurocode 8, and we will define natural vibration cases and explain all the different calculation parameters you can set. We will perform an equivalent static force analysis. We will define response spectra in accordance to Eurocode 8. We will apply accidental torsion. We will use the export options available, and we will use a new feature which is the selection of mode shapes. So we get started. We just go into the RFEM, and I wanted to give you an overview of the modules first of all. Now I'm a bit confused because of the delayed start. So I want to give you an overview of the dynamic modules first of all before we go to the RFEM module. So the basic module is the natural vibration module. This is what you always need, and it performs an analysis of frequency and mode shapes for members, surfaces, and solid models. You can directly import masses from load cases. You can build combination of masses in so-called mass combinations, and you can import stiffness modifications, axial forces, failing or deactivated members, or stiffnesses from RF concrete as initial conditions. So these are just a few examples. We have 4 eigenvalue solvers available, which I explain more in detail when we go through the example. Based on this basic module, you have the RF-DYNAM Pro forced vibration. This can perform a time history analysis and can perform a multimodal, multi-point response spectrum analysis. So this is quite a large module, and we are not going to talk about this today, as it will be in one of the later webinars this year. So you get, for example, results versus time in a so-called time course monitor, just as the example. The second module, and this is what we use today, it's RF-DYNAM Pro equivalent loads. This is based on a multimodal response spectrum analysis, and this module explicitly generates equivalent static forces, so you get load cases and result combinations exported from this module. So, and now it's time to switch to the RFEM. Where is it? It's here. So that's the structure we want to look today. So this is a simple framework, and you have 2 identical floors. They are made of steel columns and beams, and you have 2 concrete slabs, and we have defined an opening up here as well. So the 2 floors are identical, and we have some generated loads here defined. You can either display them connected, as you see here, or you can also display them separately. I have defined load cases already. You have a load case self-weight, imposed load top level, imposed load bottom level. I separated these 2 for a dynamic reason. So when we build mass combinations later on, we have different combinations factors for the top and for the bottom level. So that's why I separated these in 2 different load cases. Then we have a wind applied in X direction, wind applied in Y direction, and the imperfections towards X and towards Y. So these are load cases which are usually used for a static analysis. Our main interest is the self-weight and the imposed loads today. I have not built any load combinations because we really want to concentrate on the dynamic analysis today. So we want to open the RF-DYNAM Pro. I've put it into the favorites here, but you find it somewhere down the list usually, or you can open it via the add-on modules menu, go to Dynamic, and then RF-DYNAM Pro. So that's the first window you see, and here you see clearly the three add-on modules again. You have natural vibrations, forced vibrations, and the equivalent loads. So we are looking to the top and to the bottom one today. We start with the natural vibration analysis, enter all the input data, and have a look to the result tables then at the end, before we come back to the module and start with the equivalent load analysis. So I activate the mask combinations as well because we want to use them. So and now you see all three tabs that belong to a natural vibration analysis. So you have the mask cases, the mask combinations, and the natural vibration cases. We start with the mask cases, and I talk through the tab first of all before we then finally create the mask cases we need for our example. You can, RF-DYNAM can automatically use the self-weight, apply the self-weight of a structure. You can import masses from load cases or from load combinations, depending on what you have. So all the load cases are available. You can, in addition, you can define nodal masses, line masses, member masses, and surface masses. So these are the tables which are known from the old dynamic module as well. So you can write a list of nodes in here manually, or you can pick them graphically by using this button. So I just make an example. It's this, click OK, and then I can enter any mass here. This is, for example, for a heavy machine you have somewhere. So you can also define mass moments of inertia, which would then be a simplified rotation of the machine, just as an example. So in analog, you can define line masses, member masses, and surface masses. We don't want to do this. I clear these checkboxes. Just a wee note on the right-hand side, you see the sum of masses. So you have the nodal masses, which we have just entered, as 1,000. You get always the sum of masses separated into self-weight, components of load cases, and so on. So we don't need this. I clear all these checkboxes, and we create our first mass case, which is the self-weight. And I import it from the self-weight load case we have defined. As I activated the self-weight in the load case calculation parameters, I have to clear this checkbox up here, because otherwise I would double the self-weight. This is quite important to note. I can calculate the masses just to double check. So, and you also get the center of total mass provided here at the bottom. We can have a look into the details. There are some mass conversion types that you can apply. So you can import only the Z components of your loads in both the Z directions, or you can import the Z components of loads only in the direction of gravity. And in our case, the direction of gravity would be in the plus Z direction. If you define the Z-axis showing upwards, it would be the negative Z direction. So it's the direction of gravity is always showing downwards. You can also use the option full loads as mass. For example, if you have loads only in X direction defined and you still want to use them, still want to import them as masses, the only way to import them is to use the third option down here. So we are happy with the top option because our loads are showing in the Z direction. So here you can change the acceleration of gravity. Obviously, this is required to convert from loads to masses. Okay, so I have imported the load case 1. I've entered the description up here. I've double checked my masses. This is my first mass case, so I create another one and I call it impost load from the top level. So I clear this checkbox, I import this load case, the impost load from the top level, and I change my mass case type. You have many mass case types here available. They're getting important when we then combine the masses into mass combinations. So the roofs are the category A and B in our case, and we have the top level, so that's the roof level with a value of phi is equal to 1. So these are the values in accordance to Eurocode 8, which are provided here. So, and I copy this one to create the last case. This is again wrong now here, so I have to activate from force component off and clear this checkbox. And I copy the existing case and change just the name up here from top to bottom. And I change the load case I want to import. And I can double check the masses, because as I said earlier, these two floors are identical, and also the loads we applied are identical. So we have 16,500 kilograms here, and it should be the same in this load case. Yes, it is. So this is all we have to do for the mass cases. Now we want to combine them in mass combinations. So that's a mass combination where we combine self-weight and imposed loads. And I just want to enter them all. And you see here, note already the factors. Probably I did something wrong. I didn't change the category. I didn't change the mass case type, because this is not a roof level. This is an independent level with a value of phi is equal to 0.5. So I have to do it again. Just get them in again, and you see the combination factors here, which are preset, and they are preset in accordance to Eurocode 8. So I go back to my slides to explain this. So in accordance to Eurocode 8, you have to consider masses resulting from the permanent loads and masses resulting from any imposed loads, and where the value of CE is composed of a value of phi in accordance to Eurocode 8 and a value of C2, which is known from the Eurocode 0. So categories A to C, if it's a roof level, then the value of phi is 1, and if it's any other independently occupied story, it's a value of 0.5. And just to show you the values of C2, so that's the last column here, we have to apply a value of 0.3 in case of a category A and B. So that's our mass case type. So we have to calculate 1 multiplied by 0.3 for the top floor, and for the bottom floor we apply the 0.5 here. So 0.3 and 0.05, we have a look again to our RFEM, and these are indeed the values RF-DYNAM Pro applied. In case you are working in accordance to any other international standard, you can just change these values either by choosing a value from the drop-down list, or you can enter a value here and apply it with the tick button. So that's our mass combination. Now we go on to the natural vibration case. We want to calculate 30 eigenvalues, basically just because we don't know anything about the structure yet. So, and it's not a huge structure, so we don't have to be that careful how many eigenvalues we calculate. So to be on the safe side, I think 30 values is a good size. So we have to decide which masses are acting in our natural vibration case. So I switch to the mass combinations. The mass combination 1, which we just defined. And here you define in which directions the masses are acting. So, and I have to explain this in combination with the mass matrix. We have 4 different types of mass matrices available. We have the diagonal mass matrix, which is the simplest form, and that only considers translational masses, so masses in the direction X, Y, and Z. So it doesn't matter if you clear or activate these checkboxes in case of a diagonal mass matrix. What is considered, we go back to the mass cases, in case you have nodal masses defined and you define mass moments of inertia, these are considered also when you use diagonal mass matrix. We don't want to apply this right now. Go back. Then, so to emphasize again, you won't get any torsional modes, for example, if you just apply a diagonal matrix. You can choose the diagonal matrix with torsional elements. This means basically that in case of this member, the masses about the z-axis are considered, and in case of a member in this direction, the masses in y direction, about the y direction, are considered. So these checkboxes have an influence, but it depends on the direction of the member. And you will get torsional modes of single members. The consistent matrix is the most complex one, but also the most accurate one, because it considers all the rotations of all masses about the center of mass. It also leads to, obviously it leads to more eigenvalues and mode shapes you get. So in most of the cases, and especially in such a system, we have here the diagonal matrix is exact enough and it's good to use. The unit matrix is just for, basically this is for, you can double check the stability of your system by applying a unit matrix, but I don't want to go in any detail here. So we apply a diagonal matrix. So in our case, it doesn't matter if these checkboxes are cleared or activated, so I just clear them. And you have the scaling of mode shapes in this frame. The top three are just for displaying reasons. So it's really a matter of what you like. So you could include the rotations and the translational parts of the mode shapes, and the maximum is set to 1, or you can only use the translational parts. So we choose the top one. This is just for illustration. And the last option gives you modal masses of 1 kilonewton. This is more a mathematical approach, and this is used internally anyway when you when the equivalent loads are calculated and so on. So we use the first option. The solvers, the eigenvalue solvers. This is more or less a choice and depends on the size of your system. So the root of the characteristical polynomial is for small systems where you want to calculate all the available eigenvalues. The Langkos solver is a fast algorithm suitable for medium-sized structures, and the bottom two, the subspace iteration and the incomplete conjugate gradient iteration, these are for large systems, and really be careful to use them. They might be very slow. So especially the incomplete, the ECG iteration, it calculates the eigenvalues each after the other. So this is a very slow process and only recommended for huge structures. This button here just links to the finite element mesh settings of the main program RFEM. So this is just a short link. And this part here allows you to import axial forces, stiffness modifications, and extra options from any load case or from any load case combination you might have defined. You can also apply global stiffness modification. To make this a bit more clear, we have a look into the calculation parameters of load cases. We are talking about the checkboxes on the right-hand side here. So you can modify materials, cross-section, and member parameters. And you can also modify stiffness and have some extra options. So 2 additional tabs are opening here. So here, for example, you could deactivate any member, surfaces, or solids. And here you could import stiffnesses from the module RF concrete. So in case you want to apply something like this, you can import it into RF-DYNAM Pro using this option over here. So you can activate and import it. So also the axial forces from any load case are imported. So this is used, for example, when you have pre-stress in cables. This is quite a good example. So this is quite a big tool, but keep in mind these are only initial conditions. So this dynamic module still only performs linear analysis. These are initial conditions. So that's all we have to do to calculate our natural frequencies. 30 eigenvalues, and I just click OK and calculate, and it should be quickly done. And we have a look to this results first before we go ahead to perform the equivalent load analysis. So this is done. I have to increase the table size now because the results of RF-DYNAM Pro, they are embedded in the main program RFEM, so I have to decrease my graphic. And in case you're working with two screens, you can just move the tables around and move it to your second screen, and by double clicking you just lock it back in. So in my case I'm using just one screen today, so we have a bit smaller graphic. So a new button, this is the button 5, tables 5 for dynamic analysis. So here you find all the dynamic results. And in our case now we have just one natural vibration case defined. If you have more than one, then you find them here in the drop-down list. With this drop-down list you can switch in between the mode shapes, or you can also use these buttons here. So the table 5.1 gives you all the eigenvalues, angular frequencies, natural frequencies in the natural period. And by clicking through also the graphic updates. So as you see. The next tables provide the mode shapes, and there is just a matter of sorting, how they are sorted. So the first one is sorted by node, the next one by member. By clicking into the graphic, the table jumps to the right member, so that's member number 6. And the mode shapes are sorted by surface or by mesh node. Another important table is the masses and mesh points. You get here, first of all, you get the locations of all the mesh points you have, and you get the masses in translational directions. And at the far bottom of the table, you get the sum of all masses. So this is quite nice to double check the imported masses against the results. And the last table is the effective modal mass factor table. It provides modal masses. It provides the effective modal masses, which describe how much mass is actually activated by each mode shape. It is provided in the translational directions X, Y, and Z, and it is also provided in the rotational directions. The masses rotate about the center of the mass. So how this is calculated is provided in the manual, so I refer to the manual if you need any more formulas here. The effective modal mass factors is just the ratio of the effective modal mass to the sum of the total mass. So the sum is again provided in the last row. You have all the sums provided, and we can have a look to the effective modal mass factors. So this one, for example, is a mode shape which is acting in Y direction. So we have activated nearly 90% of the mass, and you see it in the graphic as well. This is a pure mode shape directed in the Y direction. And this one is in the Y direction as well, but it's much smaller. So it's just 3.5% are activated, of the mass are activated. And we can have a look further down the list, and here is the most relevant mode shape in the X direction. It's activating 91% of the mass, so this is the most relevant mode. So that's all we have. That's all to the natural vibration analysis. And now we go back into the DYNAM Pro module. And we want to perform an equivalent load analysis. So we activate the checkbox at the bottom here. And two more tabs appearing. That's the response spectra and the dynamic load case tab. So we go to the response spectra, and we have to define a response spectra which is actually used to calculate the equivalent loads. So you could define this user-defined, so you can enter values, or you can import it from Excel, or you can load and save from your own library. We want to define a response spectrum according to a standard, so that's the Eurocode 8 we want to apply today, and as I don't want to be specific to any certain country, I apply the European Union Annex. So just to show you the available list of international standards, so you have American, Austria, Italy, Spain, further down up to Australia and Chile. So these are the international standards we have so far, but this is one thing which is permanently improved and enhanced, so we will add more and more standards. So we will apply this one, as I said, and I want to apply a design spectrum for linear calculation. I want to have the standard type of spectrum. One, we define the horizontal spectrum first, and so that we get some values, I increase this here. So I don't have a specific project now, so I have just to assume a few values here. And in case you have to do a dynamic analysis for a certain project, you know all these values, and we apply a ground type of D. So we end up with an acceleration of 2.97 here at the maximum. And as I go over the graphic, you see all the values are shown, and you get the maximum and the minimum provided all the time. So you can't change anything here because this value is dependent on the peak ground acceleration and the importance factor, and you can't change these values because this is dependent on the ground type we have chosen up here. We keep the value Q. The value Q is a ductility factor, and this is just the minimum value which ensures that it's not going down to zero, the response spectrum, for large periods. You can access the values which are generated here in the table. You can adjust the time steps or the natural period steps, and you can export this to Excel. So this is now the done in accordance to Eurocode. We applied this annex, and this is the horizontal design spectrum. And now, instead of creating a new one, I copy the existing case to make sure that I take over all the parameters I've defined. So I copy the existing case, and I want to define the vertical spectrum. So I just have to change horizontal to vertical, and all the parameters are kept, and you see that the graphic is changing. Okay, that's all we have to do here. Now we go to the dynamic load cases. This is where everything comes together. So everything that you defined earlier, natural vibration cases and so on, this is combined here. So we have to assign natural vibration case. We only have one, so we don't have to do anything here. If you have more than one natural vibration case, you have to choose the correct one from the list. We perform an equivalent static force analysis. Depending on what add-on modules you have, or there might be more available. This is depending on what you checked here in the general tab. So as we only check the equivalent load analysis, this is the only checkbox radio button which is available here. So we have to define in which directions the response spectrum is acting. These are the excitation directions, and for now we apply all three directions. This is also because I want to show you some differences in what load cases and result combinations are actually exported. So this is the space where the accidental torsion actions are considered, and we keep this for later. We come back to this. Here you define what load cases and if you want to create result combinations, and the load cases are exported. They contain the generated loads, and they are exported separately for all mode shapes and for all excitation directions. So we want to export the load cases. We want to also create result combinations. This is the first step of the combination process, which combines the modal responses with the SRSS rule, so they are combined quadratically. And you have the second level of combination, which combines the directional components, either also with the SRSS rule or with the 100% 30% rule, as, for example, known from the Eurocode 8. So you could apply different factors in the different directions, and you could rotate your excitation directions, but we don't want to do this today. So we have a look to the last tab. This is the mode shape tab. And as we performed the calculation earlier, it's already available. In case you just went through and entered all your input data, you have to click the button Calculate Mode Shapes here at the bottom to calculate the frequencies internally in advance. So now we've seen this earlier. So we have the frequencies, we have the natural periods, and now this is provided together with the acceleration of the response spectrum. And you see in the graphic you get red lines where you see also the corresponding values of period and acceleration of response spectrum. And I can click through and the red lines are changing in the graphic. And here you see again the effective modal mass factors, and so the important one in Y direction, and further down the list there was the important one in X direction. And you already see the Z direction is not really relevant, and we will deactivate this later on, but as I said, I will show you the difference in created result combinations. So you have the auto select button, which just selects all of them. If I clear this checkbox, I can do whatever I want to do. I can deselect mode shapes. I can also let RF-DYNAM Pro do the job for me, and I can define an effective modal mass factor here, and RF-DYNAM Pro is then automatically selecting the mode shapes. So it's preset to 0.05 because there's a 5% rule known in the Eurocodes. But more important is that you reach the 90% here, the sum of 90%. So in our case, we need this one, and we should also use these two mode shapes because we don't reach the 90% at the moment. And the X direction is okay. We have the 91% here already, so this is enough just using this one mode shape. So I would decrease this value to 0.03 and just double check. Now this one is checked as well, and this one is activated. So this is a really nice option, especially when you calculate many eigenvalues. You don't have to select them all by yourself. RF-DYNAM Pro is doing the job for you. So that's all we have to do. And now we can perform, I give it a name, I call it without accidental torsion, so that we are not getting confused. And now we can perform the calculation. It shouldn't take too long. And then we have a look to the result tables at the bottom, and we will see what load cases actually are exported and how they are combined to result combinations. So this is already done. So now we have not only the natural vibration case available here, we have also the dynamic load case available, and we can switch to this one. And now you get tables providing you the equivalent loads separate in the X, Y, and Z direction. And you can either display this separate for each mode, or you can have it together for all mode shapes. You get the same actually because it's exported to load cases. We have now the load case 8, 9, 10, 11, and 12. So the 8 exports the mode shape number 1 in the direction Y. Here you get the mode shape 2 in the direction Y. And here in case of the mode shape 28, we see that it's done separately for each excitation direction. So you get the mode shape 28 in the direction X and in the direction Z. It depends only on if there is an effective modal mass factor equal to 0, then the load case is not exported. So it depends on if it's relevant or not. So then we have the result combinations created, separated for each excitation direction, and the 100%, 30% rule is applied. So we have a look into the added load case and combination dialog. So here you see the load cases. You can't change anything here in the calculation parameters. This is done by purpose because dynamic analysis is only linear at the moment, and it wouldn't mean anything if you perform a nonlinear static analysis with only linearly achieved results or achieved generated loads. So it wouldn't mean anything. So this way this is grayed out bipropose. So we have the result combinations, and as I said, this is done in 2 steps. So you get, first of all, you get result combinations still separate for the excitation directions, and here the modal responses are combined with the SRSS rule. So we have a look to this one because this shows it best. So we have the 3 load case inside. You can't change anything because this is just exported by EN1998-1, so you're not supposed to change anything, and these are combined quadratically using the SRSS rule, and you can either this option here is activated by default. You could also clear the checkbox and then you would apply the standard SRSS rule. I just want to show you quickly the formulas behind this. So this is the way how the equivalent loads are calculated. Don't be scared, it's not as complicated as it looks. So you have each line represents an excitation direction. So this is the excitation direction X, and you get forces in all 3 directions. This is the participation factor, the mode shapes, the acceleration from the response spectrum, and the masses. And you have here just a small word to the SRSS rule. You have the standard SRSS rule, which would provide you only positive values, so you would lose all your signs. And if you keep the preserve sign option activated, this is a modified SRSS rule which builds result combinations which are consistent in itself. So if a positive normal force belongs to a negative moment, this is kept applying this rule. So it's quite important to keep this rule. And we go back to the RFEM. So this is the default, and I would recommend to keep it activated. So the last one is the 100% 30% rule. So this just takes the 3 result combinations into account and applies different factors. So 1.3.3, and the other ones, the factors are just changed. Yeah. So we go back to the RF-DYNAM Pro module because we have to apply also the accidental torsion. We have to account for them. So what I want to do, I want to copy this case. I want to apply accidental torsion. I change just my description. I consider it, and here these are the eccentricities which are in accordance to Eurocode. These are 5% of the length of the building. So our building is 14 meter in X direction and 5 meter in Y direction, and we have to calculate 5% of 14, which is 0.7, and we have to calculate 5% of 5 meter, which is 0.25, and it might be different in different international standards. So the 5% is in accordance to the Eurocode, but it might be different in the country where you are living. So I want to show you the difference in the load cases that are exported now. So this is why I've copied the case. I want to show you the difference. So we just perform a quick calculation again. In the meantime, I can show you how the torsional moments are actually calculated. So here you see the 5% of the length of the building in X and Y direction. So this is in accordance to Eurocode in the sections as I've written it down here. And the torsional moments are actually calculated with this formula. So using the equivalent loads, I showed you the formulas earlier. So this is the last one. We go back to RFEM. The calculation should be finished. And now we see that, first of all, we see that you always know where the load cases are coming from. So there's always a note inside. This is the load case 8 is coming from dynamic load case 1 from the mode shape 1 in the direction 1. So it's always clear. The origin is always clear. And now in case of the dynamic load case 2, we have 2 load cases for mode shape 1 in the direction Y. So you get 2 load cases for each mode shape. One is in the torsion plus direction and the other one is in torsion minus direction. And let's just have a look to it. It looks terrible if you don't zoom in. You have so many loads, but if you zoom in, you see the applied equivalent loads in all 3 directions, and you see the torsional moment. And this is the torsion plus case. And if I switch to the other case, the only thing that changes is the direction of the torsional moment. So the number stays the same and the equivalent loads stay the same as well. So and what happens now to the result combinations? We have a look in here. The result combinations, you have the same here. You always know where the origin is. So that's dynamic load case 1 and that's dynamic load case 2. And here we have a look to the Y. We have now 6 load cases instead of the 3 we had earlier. We have 6 load cases and they are sorted in groups. So the plus torsion and minus torsion load cases are in one group, which means they are combined with an OR combination first, and then the SRSS rule is applied as we explained it earlier. So the second step is just the same. It's using the factors, the 1 and the 0.3, as we discussed earlier. So this actually happens with the accidental torsion. And now we just want to create a final one. So we have to consider accidental torsion in accordance to Eurocode 8. So I deactivate this dynamic load case. I don't want to solve it. I keep this. And I clear the checkbox Z direction as well. We have seen that the effective modal mass factors are all nearly 0 in the Z direction. And there's also a limit in the Eurocode, provided in the Eurocode. When the ground acceleration of the response spectrum is below a certain value, you don't have to consider the Z direction. And this is the case for our example. So I clear the checkbox and I will show you the difference in the created load cases and result combinations now. So that's the final setting we want to use. And the mode shapes, they are just staying the same. Here again, you see the 0 here, so the Z direction is not relevant at all. So I click OK and calculate. And now the final thing we have to do is to build a seismic design combination in accordance to the Eurocode 0. And we have to combine the permanent loads, so in our case that's just self-weight, with the seismic action and with the characteristic values of any variable actions, which are the imposed loads we have. And here you see again the value, the combination factor C2, which we've used earlier for our import of masses. That's the same value in the Eurocode 0 table A11. You find in our case that's a category A and B, and we have to apply a 0.3 here. The factor of C is 0.3. So back to the RFEM. The calculation should be finished in the meantime. It is. So we have a look to the final created load cases and result combinations. So I don't have the Z direction anymore. Just remember we had for the mode shape 28, we had also a Z direction which is now disappeared because I cleared the checkbox. And so these are the final load cases we have. And we have result combinations now only in the X and the Y direction. Z direction is missing. And you also only get 2 100% 30% rule result combinations, so 1 and 0.3 and the other direction. So what we have to do is, that's the only thing you basically have to do manually at the end. You have to build your seismic combination. We want to add the self-weight with a factor of 1. We want to add the imposed loads with a factor of 0.3. So the 0.3 is not available here in the drop-down list. So I enter the value manually here and apply. So I have to tick this button and I do the same here. 0.3, oops, hold on. 0.3 and I apply this. I want to change them to permanent. It shouldn't make any difference in our case, but that's an accidental combination, so it should be all permanent. And finally, the result combinations that we got from the RF-DYNAM Pro, the final one only, the 100% 30% one, and we add them selected together with an OR combination. So there are, again, you see the group, they are assigned to a group 1. I want to change it to permanent as well. And they have a factor of 1, which is correct. So that's our final seismic design combination, which we now can calculate. And just a word to the automatic combinations. Oh no, it's already done. So you can have a look to the deformations, for example, and here we go. And that's that we don't see anything. As it is a result combination, we have by default, you have the maximum and minimum values activated. For now, we have a look only to the maximum values, and we can switch here in the panel to the color spectrum. So we have a maximum deformation of 10 millimeter. So this is our final seismic design combination. And a word to the automatic combination. The result combinations that are exported from RF-DYNAM Pro are not able to be used in the automatic combination thus far. So in the general data, you could activate this one, create combinations automatically in accordance to the standard you want to choose here. So there are many available. So you could, the advice is to perform all your static analysis first, activating this checkbox and do the automatic combination as you are used to. And then you could deactivate this checkbox, so clear this checkbox, keep all the already combined result combinations, and then do your dynamic analysis, get your result combinations from the RF-DYNAM Pro, and then do the final combination as we just did. So the last step needs to be done out manually. So this one. So that's me finished with the RFEM presentation. We just have a look to the final slides. So that's us done. I hope it was a bit helpful. And you know now a bit better the new RF-DYNAM Pro module. And if you need some more information, you can visit our Dlubal website. It's www.dlubal.com, or you can follow us online, the usual things, Facebook and Twitter. I recommend the Dlubal blog. This is quite helpful in many cases. And you can always write an email or call us. And there are more webinars coming up this year. The next one is tips and tricks using the navigator and the printout report in RFEM, which will be already in April. You see it on the website. It's end of April. It's the next English webinar. And there are more webinars coming up later this year. The one I mentioned, there will be another webinar on RF-DYNAM Pro using the time history analysis. So you will hear more from us. So you can always register on our website, and I thank you very much for your attention, and I hope it was helpful, and we will answer all your questions now after the webinar. Many thanks. Bye bye.